Hello everyone, my name is Shreyas Terdalkar. Welcome to our project Red Eye Plus Shuttle Navigation System. My project mates are Harshkumar Modi, Madhuri Krishnamurthy, Mili Bimal Parikh, and myself. Let us begin. First, I will give a brief introduction about the current Red Eye system and its issues. Then, I will go through the problem statement for which the solution is proposed. Then our team will go through the implementation of algorithms to solve the proposed problem. And lastly, we'll show a brief description of future enhancements that can be done to the project and conclusion. In a world where we are at a phase of extreme global warming, we need to try our best to utilize and optimize our resources. We need to reduce our carbon footprint in society. Here at Northeastern, we have shuttle service which drops off students back to their homes after a busy day at college. The Red Eye. Our aim is to optimize the service to be more fuel, cost, and eco-efficient. Red Eye is Northeastern's premium shuttle service and navigation system, which drops off students within 2-mile radius cover. As frequent users of Red Eye, we observed few anomalies within this system. We decided to take up the task to analyze and resolve these anomalies using Red Eye Plus. So the issues that we observed were that the students are prioritized and directed to different shuttles on first come first served basis, which may end up in multiple shuttles having to cover similar routes and destinations. This results in wastage of fuel and time. Secondly, students living just outside 2-mile radius are not included. The problem statement that we boil down to is optimize the scheduling of shuttle along the nearest drop-off locations to reduce fuel consumption. We want to optimize the path algorithm and scheduling algorithm for Red Eye to make this possible. We want to find the optimal path and optimal scheduling of students to cabs dynamically to lower the fuel and distance of the service. Secondly, Red Eye has a feature that only accepts drop-off location of the students within 2 miles of campus. In order to help students with better connectivity, we would want to drop off the students at the nearest public transportation service available to the destination of the students within the 2-mile radius instead of not attending to the student at all by using shortest path algorithms. For example, from the given diagram, if there are 3 drop-off locations A, B, and C with distances 1 mile, 1.5 mile, and 500 meters respectively, where A and B are along the same direction, suppose student 1 wants to reach A, student 2 wants to reach B, and student 3 wants to reach C, and there are 2 red eyes available. Since students 1 and 3 book at the same time, they are assigned to a single shuttle and student 2 to another. Due to this, 2 different shuttles have to travel along the same direction, which could have been avoided by scheduling student 1 and 2 in the same shuttle. We want to optimize the path algorithm and scheduling algorithm for Red Eye to make this possible. Thank you.
Following to what Shreyas just explained you with the introduction to the problem, I'll now show you how we have decided the solution to this problem and implement it. The steps are very simple. We start with clustering, we go with the shortest path algorithms, and we display this into GUI. Now what do we mean by clustering? So since we showed you the problem that how one red eye and the other red eye both go to the same destination in just a difference of some time, we decided that why don't we apply clustering to the locations and then figure out that which red eye would go to which specific location. So let me show you how this works. So here we can see the destination list, which is the places that students have asked the red eye service to drop them to. Now what we want to do with clustering is to figure out which locations are accessible by one red eye and which are accessible by the second red eye, so that they don't repeat the same location one after the other. The idea is to first find the latitude and longitude of this addresses so that we can figure out and we can place them and plot them on an XY scale using the Google API We do this, and once we get the JSON format output, we find the exact coordinates from that. As it is done, we now have an input from the user now to determine how many red eyes we have. This is so that we can define the number of clusters of in which we need to divide the destinations. So as we start, we right now put an input of 3 red eyes, which means we have 3 red eyes available, and then 3 can go to each different path, which means we can divide our destinations into 3 clusters. Upon running the steps, we can see that we have the destination name, the coordinates, and the cluster in which it is divided. This clustering is done by k-means, which follows a simple funda. It tries to find a centroid and assume a point to be a centroid and finds the nearest distance from to all the points. Once it finds the optimum centroid, it divides the clusters on this basis, with the distance with each cluster belonging to certain centroid. Using this, we are able to find that yes, we have 3 clusters in which the destinations are divided into 0, 1 and 2. To clearly show you this output, we then divide this into lists, which each list defining the cluster, and the destinations are adjusted according to that clusters. Our next step is to now find the path to each of this destination. Now to make a fully connected graph, what we do is take each cluster, and in each of that cluster we find a destination from one point to another. As we want to make a well connected graph to figure out what will be the optimal path, as each destination can be connected to the other destination, we start with we form a well connected graph. To do this, we take out the distance matrix, we define it, and using the Google API we find the distance of each point to the other point by the exact roadways and the flow of traffic and the rules allowed. So with this we find the exact destination in a JSON format and return it, to which we can see this as an output in this form, where each point is connected to the other point and the distance is exactly the road distance we need to cover to travel to that place. This way we are able to make a fully connected graph and then apply our shortest path algorithms next.
So once the clusters are generated, using that as the input, we have implemented the shortest path algorithms on each of these clusters using Bellman-Ford algorithm, Floyd-Warshall's algorithm, Dijkstra's algorithm, as well as traveling salesman approach. So in Bellman-Ford algorithm, we compute the shortest path from a single source to all of the other vertices in the graph. So in our case, vertices are the drop-off locations, and the weights in the graph represent the distance between each of the vertices. So Bellman-Ford uses a dynamic programming approach to compute the distances between the vertices. So for implementation, we have a distance array which initially is initialized to infinity, except for the source, which is 0. We relax all of the vertices one by one, v minus 1 times, meaning the number of edges of all the edges are relaxed one by one. So in each iteration, we will be calculating the sum of distance, which is currently at the source, plus the weight of the edge. If it is lesser than the distance of the destination, then we update the distance. So finally, the distance array would have the shortest path from source to each of the vertex. Since we will be running the loop v minus 1 times, that is the number of edges for each vertex, the time complexity is order of v into e, where v is the number of vertex and e is the number of edges. Floyd-Warshall's algorithm is also a dynamic programming approach to compute the all-pair shortest path between the vertices. So here we consider each vertex as an intermediate node and compute the shortest path between two nodes. So here we have a 2D matrix which initially consists of the distances between the vertex, infinity if there is no direct edge between the vertex, and 0 for the diagonals. Considering each vertex as an intermediate node, we'll calculate the sum between these two vertices. If it is lesser than what is already present in the matrix for that vertex, then we update it. So finally, after the loop runs, we will have a 2D matrix with minimum distance for each of the other vertices. Since it's run for every vertex multiple times, so the order of the time complexity is order of v cube. So in terms of code, so this is the main logic for Bellman-Ford. So this is the distance matrix which is initialized to infinity, except for the source. And for each of the distance, sum of the distance with the current one plus the sum of the edge, if it's lesser than the distance at the destination, then we update it. We also update the parent to keep track of the path. So similarly, Floyd-Warshall's algorithm also consists of a 2D matrix initially, and we run through each vertex considering it as an intermediate vertex for all the other vertices. So if the sum of the intermediate vertex with the source and destination is lesser than what is present for that vertex, we update it. We update the distance. Along with that, we also have the path for this vertex. So when we run this algorithm, so this is for each cluster we're running the algorithm. This is one cluster here, there's another cluster here, and one more over here. So there's Bellman-Ford running for this. So the first one is the source, then is the destination and the distance. So from 0 to 1, it took 2.3 miles, and this is the direct path between it. It can also be possible that it's through something else. So here the source is 0 and the destination is 1, but the path is through 11, which is the shortest of 1.5. And for Floyd-Warshall also similarly, source is 0 to 1, 2.3 is the distance, and 0 and 1 is the path. So for each of the clusters, these are calculated. And
So I'm going to be explaining the Dijkstra's algorithm and its implementation for our project. Dijkstra's algorithm is an algorithm to find the shortest path between the vertices in a graph, and the main application for this is in road networks and in Google Maps. For a given source in the graph, the algorithm finds the shortest path between the node and every other node. For the implementation, we initialize all the vertices to infinity, and we set the Snell library to 0 because that is our starting node. Next, we iteratively choose the smallest value node and set it as the current node and visit all of its neighboring nodes. Here, by nodes, I mean all the destinations of the that the red eye has to reach to, and the source node is the Snell library, and the edge between these nodes have a weight which is actually equal to the distance between the two nodes. Once all the current node's neighbors are visited and their distance is updated, then we mark the current node as the visited node and add it to the visited array. We repeat all of these steps until all the vertices are added to the visited array in the graph. The time complexity for this algorithm and its implementation is O of E plus V log V, where E is the number of edges and V is the number of vertices in the graph. Let me quickly show the code. So in the code, we have a class graph and we have a constructor for the graph that initializes the vertices, edges, and the visited array. Then we have a function to add the weight to each of the edges between the destination nodes. Then we have the implementation for the Dijkstra algorithm, and this returns a dictionary. The key values in this dictionary are the destination of the red eye, and the value is the shortest path from Snell to that particular source node. So after implementation, I have ordered the dictionary in such a way that it gives us the order from Snell library to all other vertices. So this is our final output for each cluster of vertices. It gives us the output in a way that it gives us a path from Snell library, which is 0, to all other destinations in the order in which the red eye needs to travel. So from 0 it goes to 2, 3, then 5, 4, and 1. Similarly, for other clusters, we have similar outputs. Next, we have the traveling salesman problem implementation. So for traveling salesman problem, the problem is to find the shortest possible route that visits each and every city or destination exactly once and returns back to the starting point. This traveling salesman problem is an NP hard problem, and the implementation goes in such a way that we need to generate n minus 1 permutations of the destinations, where n is the number of destinations that we have. In our example that we have taken in the project, we have 19 destinations, so we need to generate 18 factorial permutations. Then we need to calculate the cost of every permutation and keep the track of minimum cost permutation. Finally, we need to return the permutation with the minimum cost. Since this algorithm runs n factorial times, so the time complexity for this algorithm is O of n factorial. For this problem, the traveling salesman problem implementation actually runs for 46 minutes, and it calculates 18 factorial permutations of the destinations, and that's why it takes a very long time of 46 minutes to run this code, and hence we cannot really apply this algorithm in a real life situation.
Step 3, Graphical User Interface using Python Kinter library. Why did we use Python? As a team, we realized that all of us has extensive experience in using Java. Therefore, we wanted to try something different and learn something innovative. Therefore, we decided to go with Python for our project. Python perfectly blends data science tools with object-oriented design required for this project. It is relevant, widely used, easy to learn and readable. Why did we use Kinter? Python's de facto standard GUI is built in Kinter library. It is included with standard Linux, MS Windows and Mac OS installs of Python. Visual elements are rendered using native operating system elements. This is a screenshot of the graphical user interface developed for this project. The left-hand side shows output for Dijkstra's algorithm, whereas the right-hand side shows the output for Bellman-Ford and Floyd-Warshall algorithm. Future scope. First one, resolving 2-mile limit issue. Students living just outside 2-mile radius can be dropped off at the nearest T station. This is the next thing that we want to achieve should we continue this project and further. Seating arrangement. Students can be assigned seat number so that the first student to be dropped will be seated at front. Similarly, last student to be dropped can be seated at the back. This is something that we have observed during our trips from radar. Number 3, other clustering algorithms. Currently, we are using K-means clustering algorithm, but we can improve this by using other clustering algorithms like Kruskal's clustering. So this was our project. Thank you so much.